Okay, well, if you're hearing this, then my internet has failed and I'm unable to give the talk in person. My name is Luke Clifton. I'm from the reflectometry group at ISIS. I'm going to talk to you for around the next 5 minutes on work myself, Rob Dalgleish and John Webster have been doing on looking at upgrading the CRISP reflectometer to become a composite neutron reflectometry and lamellar diffraction beamline, and in particular looking at what is required to engage in lamellar diffraction studies on this instrument. So CRISP is a relatively old beamline now. It was globally the first dedicated neutron reflectometry instrument and was on the ISIS user program for from I think 1988 to around 10 years ago, where it was taken off the user program to allow staff from the reflectometry group to concentrate on developing the Target Station 2 reflectometers, because CRISP was relatively uncompetitive compared to these beamlines due to lower flux and a high parasitic background. So myself, John and Rob have been looking into what we would need to do to bring CRISP back onto the user program, and in particular what new science capabilities we would want the beamline to have if it was brought back. And one of those was lamellar diffraction capabilities. So lamellar diffraction is a technique where you illuminate a multilamellar stack of biological membranes on a solid support surface. You measure the Bragg reflections that come from this in the QZ direction, and you use those to and you directly convert those via Fourier summation into a one-dimensional density profile of the biological membrane. And what the technique offers that reflectometry, neutron reflectometry itself doesn't, is a near atomic description of the internal structure of biological membranes. So here you can see some examples of data from a single wavelength machine. So this is from a paper by Shokuyan at SNS. And here we can see some data showing the one-dimensional density profile across the membrane from some work done by Kent et al. In this article. And here we can identify methyl groups, the aliphatic CH2 chains, and their bilayer head groups of a model biological membrane. And here we can see the location of a cryopreservant, in this case trehalose, on the outside of the membrane. So you can see you get this nice, very defined definition of the individual components of the lipid bilayer across the membrane. So the first thing we did in our upgrade project was to look at how CRISP in its current configuration performs as a lamellar diffraction beamline. Now CRISP has two real advantages as a lamellar diffraction beamline that would make it unique. Firstly, it's a horizontal geometry instrument, whereas most lamellar diffraction beamlines globally are vertical geometry instruments. And the horizontal geometry means that you can study very fluid membrane stacks without worrying too much about gravity effects. Secondly, it's a white beam instrument, so you can get a large QZ range from a single angular measurement. And this means potentially, with the right upgrade and the right flux increases, you could measure the samples very, very fast. So it could become a very, very high throughput instrument for this kind of study. But the first thing we did is look at how the instrument performs currently. So we got DPPC, it's a very commonly used saturated phospholipid. We put it onto a silicon wafer, and we produced this sample, which looks a little bit different from the sort of samples I usually make, which are usually planar membrane samples, single membrane samples. And we measured it on CRISP, a number of angles and a number of different isotopic contrasts. So we measured it in D2O, HOD, so 50% D2O, 50% H2O, and H2O. What we found using the linear detector, which is currently on CRISP, which was, I believe, a prototype for the interlinear detector, is that actually the instrument performed okay. It wasn't terrible. We managed to get some pretty nice data on the linear detector showing multiple Bragg reflections from our sample, and we found at around a theta of 3.8, we're able to obtain 5 individual orders in one for one angle. So we have that's the first order, second order, third order, fourth order, and there's the fifth order there. Using some background subtraction techniques and diffraction focusing in Mantid, we were able to reconstruct these diffraction profiles in the QZ direction, under multiple different isotopic contrast conditions, and then using Fourier synthesis, we were able to construct the following density profile of our DPPC membrane. We're able to write some scripts that sit within Mantid that allow you to phase the individual isotopic contrast, to allow you to phase the individual Bragg reflections based on the individual isotopic contrast, which allows you to resolve these profiles without the need for modeling, which is quite neat. And the data we got is not bad. Okay, it's a little rough around the edges compared to other stuff that's published, but we're able to identify our lipid head groups, our interbilayer water, our methyl groups, and our aliphatic chains. And so we're able to show, even in its current configuration, CRISP can actually undertake this kind of study with the advantage of being a white beam instrument and having a horizontal geometry. But to really make CRISP competitive as a lamellar diffraction beamline, or as a composite lamellar diffraction beamline neutron reflectometry beamline, we want to make the following upgrades to the instrument. So we want a new instrument guide coming from the target, a new area detector, so a more modern area detector, evacuated flight tubes between each of the slits, a new blockhouse or background upgrade so that some of the shine off the floor is reduced, so some sort of upgrade to reduce the background, which is a real problem, new course jaws, modern collimation slit set. So currently I think the old inter jaw sets are on there, and so we want to replace those with much more modern slit sets, a new sample stage, and some dedicated sample environment. I've put a little star next to that because that's actually being developed at the moment, because currently there's lamellar diffraction taking place on Llama as well. So they're having sample environment developed for both Llama and CRISP. I should also say that to bring the instrument back onto the user program, we would need one new instrument scientist with a specialism for this kind of science. Otherwise, we'd have to move someone off of other programs to look after this kind of science area, and that's like robbing Peter to pay Paul. So what sort of science do we get with this upgrade? And the upgrade is going to cost approximately 4 million for all those upgrades to the instrument. So we gain an instrument that allows you to understand near atomic level of details on lipid behavior in biomembranes. And a good example of this is some work by Leonard et al., where they looked at the location of cholesterol within membranes. The upgrade allowed you to look at precision details of small drug interactions with biomembranes, so much more precision than we get currently with NR. And a great example of that is the work that Fabrizia Foglia and Dave Barlow did on and their co-workers did on amphotericin, an antifungal drug. We gain a direct a way to look at native biomembranes with near atomic precision, and in particular look at skin, which is an area that's been studied quite a lot with this type of technique. So you can see the stratum corneum membrane within skin. You will work out the relative distribution of lipids and components within that membrane and look at how they change, say, when you add a cream or you add a drug that crosses the skin barrier. Okay, just to finish, I would like to thank, obviously, John and Rob, who I've been working on this project with, but also we've had steering advice, a lot of advice from Dave Barlow, who's been helping us a lot with the project and giving us advice to help us move forward. Bruno Demi from the ILL, who's been doing the same, giving us lots of technical advice on how to run this kind of instrument and what sort of studies are done. And Fabrizia Foglia from UCL, who's also been helping us by steering us on this project. And I would also like to thank you for listening.